Yay!
Yay! All right, here's another standard example. Here we will try to compute the tension in a cable that's holding up a load. We've got some sort of boom that can pivot over here at a wall, right? So here's our wall, and here's the boom, and it can pivot right there. And I want to find what the tension is in that cable, and it's holding up some load, right? And the boom has some weight, 150 newtons, let's say. Okay, so how are we going to do it? What we're going to do is, the trouble is we don't know all the forces in the system. I mean, it still must be true that the sum of the forces are 0 and the sum of the torques are 0, because we don't want this thing to accelerate or spin or anything, right? We want it to remain steady. So it's still true that the sum of the forces have to be 0, some of the torques are 0. I don't know all the forces in the system. In particular, it looks like, I mean, maybe you do know. I mean, we're trying to find the tension, but the main force that we don't know yet is this one. We don't know the force over here at the wall, because there's got to be some force there. I mean, imagine if this thing is holding up some load and you put your hand in between the boom and the wall, your hand's going to get crushed. So there, for sure, there's going to be some force over there on the wall. So we might need to figure that out eventually, but I don't know what it is yet. So let's start by summing the torques about that point, right? Because here's the strategy. If I sum the torques about the wall to be equal to 0, that zeroes out that force that I don't know, because it's 0 units away from the wall. Okay, so let's do that. So let's sum the torques about the wall so I don't have to worry about that force that I don't know, and then I can solve for T. All right, so here we go. This implies, let's see, there's going to be 3 torques in the system. There's the weight of the bar. The weight of the bar, the weight of the boom itself is trying to make the boom rotate clockwise. That's going to be a negative. So we're going to say that that's going to be a minus. It acts at the center of mass of the boom, which is 2 units away from the center. I said that it looks like that whole boom is like 4 meters long. So this is going to be like 2 times 150 with the minus sign in front. I've got the load, the big M, and that's acting out 4 meters away. So that's also going to have a minus sign. So that's going to be 4, because it's trying to make the boom rotate clockwise. So it's 4 times 300. And then T all by itself is trying to make the boom rotate counterclockwise. So that's a positive. Right? So it's going to be T, and that also acts 4 meters away. But it's not the whole T. Remember, what we want is that perpendicular component of T. And the perpendicular component of T is going to be T sine theta. That's the bit that actually matters. Because the cosine theta part, the x component, is headed back towards, it's headed back along the boom. That's not making the boom rotate at all. So it doesn't give a torque, right? So there we go. So this equals 0. So now I can solve for T. The way that we've drawn this, that's like a 3, 4, 5 triangle. So sine of theta is just going to be 3 over 5. If you look at the triangle, 0.6. So it looks like I have everything I need to solve for T. And if you do that, if you solve for T, what you're going to find out is that T is, what did I get? T is 625 newtons. Cool. Well, look what I can do now. Now that I know what T is, now I can say that the sum of the forces in the x direction are 0. Because, look, that T in the x direction, the x component of T, is going to be just equal to the x component of the force on the wall, or really the force on the boom, right? Because there's going to be this. This is the one I'm talking about. There's the x force for the wall, there's the y force in the wall. So it's the x one that I'm interested in right now. So this is just going to be, what letter did I get? Force from the wall in the x direction minus t cosine theta, the x component of t, has to be equal to 0. So the x component of this force is just going to be t cosine theta. So t cosine theta is 625 times cosine theta. I think I got 500 newtons. There we go. And now I can get the y, right? So some of the forces in the y direction are also 0. What forces do I have in the y direction? I've got force wall y. That's going in the positive direction. And then I have minus 150 minus 300 equals 0. So, oh, and then t, oops, I forgot one, didn't I? Oops, let's get rid of this. I've also got a plus t sine theta equals 0, because the y component of t is also pointing up. Okay, so if I do that t sine theta and I put those numbers in, I get F wall y is 75 newtons. Cool. So now I know the force acting on the pin. So the force, the wall, is just going to be 500 in the x, 75 in the y, newtons. I mean, if you want, you can multiply this out. I think I got 505.6 newtons at, it was something like 8.5 degrees, 8.5 degrees, something like that. So anyway, we could figure out what the force on the boom is from the wall. So it's mostly in the x direction, just a little bit in the y. So the whole force is, I don't know, it's coming off somewhere like that at like 8 degrees. Okay, so that's sort of a common technique. It's sort of a common trick, is what you want to do is sum the torques about a force that you don't know, because that kind of zeroes it out in the torque equations. Solve for some force like the tension, and then using the force equations, now I can go back and figure out what the force in the wall is because of the condition of static equilibrium. So that's sort of an overall strategy for doing these things.